Welcome, everybody. Thanks for joining today. My name is Jennifer Griffith, and I work at NWMOA, which is the Northeast Waste Management Officials Association. We're an interstate association that were formed by the governors back in the 1980s, the governors of the 6 New England states, Connecticut, Maine, Massachusetts, New Hampshire, Rhode Island, and Vermont, and then subsequently New York and New Jersey both joined NWMOA. So those 8 Northeast states work together on different waste-related issues. So the solid waste programs, the hazardous waste programs, the toxic use reduction and pollution prevention programs, and then also the waste site cleanup programs in those 8 states sort of coordinate and work through NWMOA. And the priority of the waste site cleanup programs is training. And PFAS is, of course, a big topic. So that's what we're doing here today, having some training. We've got 2 great presenters, well, 3, 2 great presentations with 3 presenters. We've got Dr. Jennifer Harfmann from New Hampshire DES, and then also Jasmine Stefansky and Brittany O'Brien-Drake from the New York State Department of Environmental Conservation presenting today. And I'm showing the NWMOA website here because after the presentation, I'm just trying to move this control panel out of the way so that I can do things. You should, we will be posting the presentation. So I'm showing the NWMOA website so you could go there and look yourself at more about NWMOA and all the things we do. But to find the presentations afterwards, you just click on events and then scroll down. The events is all forward looking. Naturally, this website just looks forward. And so here's our webinar for today. But pretty soon it will be in the past. So to find past events, you need to use this little arrow right here. And then you switch to a different time frame, and you can see all the webinars and things that have occurred since this is showing since August. So there's a bunch of these NWMOA webinars. Eventually, this webinar will be down here, and you can click on it. I will just show you what it would look like afterwards. So you would click on, we had just last week presentations on background studies. So what happens is the presentations get linked. So they'll be here, and then the recording will be down below. So, and it chooses, I haven't taken the time to put a different, anyway, it chooses whatever thing. Things look interesting. So that's just to let you know where you'll be able to find the presentation afterwards. I will also be sending an email out to everybody afterwards. So there are a lot of people on the webinar today, which is great. But if you want to ask questions, you're going to need to type them into the question box. So everybody has a control panel, and there's a question section, and you can just type in your questions. You can type them in at any point. You don't need to wait until it's question time in order to type in your questions. And then I will be looking at those and ask the questions of the presenters. So we're gonna, Dr. Harfmann's gonna go first, then we'll do some questions for her, and then Brittany and Jasmine will go. And then at the end, we'll have questions for them, as well as if we have time, maybe some other questions left over from the beginning. So, hopefully that works for everybody. So type your questions in at any point. One last thing is that we are getting Massachusetts licensed site professional continuing ed credits for these webinars. And as a piece of that, there are poll questions oops, sorry, that's my phone here. As part of getting your credits, if you want them, you need to do a few things. One is to stay on the webinar the whole time. Another piece is that the GoToWebinar software, this is something for everybody to know, can tell If you're doing something else on your computer and you're not looking at the webinar as the top layer on your computer, so, and I will learn that afterwards, and I won't give you your continuing ed certificate if you haven't, if you don't have a high enough score. So you really need to keep the webinar as the top layer on your computer, and you need to answer. We're going to have some poll questions that will come up, and you're going to need to answer all the sets of poll questions. And it would be good if at some point during the webinar, if you want the continuing ed credits, that you also typed in a question yourself. That's also something that you're supposed to do. So I think that's it here for me. So just a reminder, we will be posting the presentations afterwards, and I will be sending an email out with a more direct link to the website for that. And you should type in your questions at any point. So with that, I'm going to introduce our first presenter and change over the controls here. So Dr. Jennifer Harfmann is the PFAS discharge specialist at the New Hampshire Department of Environmental Services. She specializes in source attribution and reduction of per and polyfluoroalkyl PFAS, we all know that, in wastewater discharges to the ground and groundwater. She has a decade of experience in water chemistry research, studying the fate and transport of organic and inorganic contaminants in both groundwater and surface water. Oh, sorry about that. She holds PhD in environmental chemistry from the University of California, Davis, and a BA in chemistry from Skidmore College. So with that, I'm going to mute myself and turn off my camera and take it away, Jennifer.
All right, thank you. Can you see my screen, Jennifer?
Yes, I can see your screen. Yep, you're all set.
Perfect. So thanks for the introduction. As Jennifer mentioned, my name is Jennifer Harfmann. I work for NHDES in the Drinking Water and Groundwater Bureau, and today I'd like to discuss some of the work that we've been doing pertaining to PFAS in domestic wastewater. So I want to start with just a little bit of background on PFAS in New Hampshire. So New Hampshire currently has ambient groundwater quality standards for 4 PFAS: PFOA, PFOS, PFNA, and PFHXS, all between 11 and 18 parts per trillion, or nanograms per liter. And we have a pretty robust private well sampling program that has allowed us to sample over 7,000 private wells across the state. And you can see on the map on the right here, some of that groundwater quality data where we see detections in green and then exceedances of our standards in red or black. And what you might notice is that we see quite a bit of contamination in the southern half of our state. Some of this is associated with the Pease Air Force Base in this cluster over on the seacoast, and some is associated with the Saint-Gobain Performance Plastics manufacturer that has been located in Merrimack, New Hampshire. We also have some other sources of contamination across the state from waste sites, including landfills and septic lagoons, and then some other aqueous film-forming foam releases and some industrial facilities. More recently, NHDES has been looking at the potential for smaller commercial facilities to be contributing to PFAS in our groundwater through discharge of the wastewater to septic systems or to the ground surface. So we have several types of businesses that have these septic systems, including carpet cleaning businesses and marinas, both of which we have done some sampling in that wastewater and have found PFAS in the wastewater, and therefore has the potential to contaminate surrounding wells. We've also been doing some sampling of floor stripping and refinishing wastewater, particularly at schools that have septic systems, and strip and wax the floors on an annual basis. And then that wastewater is discharged to those septic systems and could contaminate nearby wells. We have a, if you're interested in that work, we have both a one-page summary and a more lengthy technical report on that work that is posted on our PFAS investigation website on the groundwater page. But today what I'm going to be talking about is domestic septic systems. The majority of our state, the population in our state, has a household septic system. And we have found, as I believe many other states are finding as well, instances such as this, where we have residential neighborhoods where there are no known sources of PFAS, but we see detections and in some cases exceedances of our standards in the groundwater. So we're turning to look at domestic PFAS and domestic wastewater as potentially contributing to some of the PFAS that we're seeing in the groundwater. Now, if we think about the wastewater that is typically generated in a home, a lot of that wastewater is centered around cleaning. So we are doing laundry, cleaning clothes, cleaning surfaces, so floors or carpets, washing dishes, washing our hands, showering. All of these activities use soaps or detergents or other cleaning products that generate wastewater or that may contain PFAS because of the properties that PFAS imparts, and therefore the wastewater that's generated from those activities may also contain PFAS. So to explore this idea, we are interested in trying to understand what a typical domestic PFAS load to the environment looks like. We have been sampling wastewater at a residential community that has a combined septic system. And so the wastewater that's generated at that location is entirely domestic, so there's no commercial or industrial inputs. So we're trying to characterize that wastewater effluent so that we can understand domestic sources of PFAS. So here's an aerial shot of that particular community that we have been focusing on. There's 24 units in this community, and each unit has its own septic tank, primarily for solid settling. The wastewater from each of those septic tanks flows by gravity down to a lift station, and then is pumped up to a nitrification denitrification treatment system. This treatment system was installed to reduce nitrate levels prior to discharge of the wastewater. And this treatment system consists of a septic tank for some additional solid settling, and then two other chambers that contain a plastic honeycomb media that is seen here. That media acts as a substrate for bacterial growth, and the wastewater flows through and is aerated to allow for nitrification, and then undergoes anaerobic denitrification prior to discharge to one of 3 leach fields that are located here on the property. Now, since we are primarily interested in the wastewater that is discharged to these leach fields and to potentially groundwater, we have chosen to sample at that point of discharge, right at the tail end of that treatment system. We have collected monthly grab samples of effluent at that location starting in January 2023, and this is ongoing, so we are continuing to sample. I'll be showing results through October of this year. And primarily we have been analyzing using EPA 1633, so giving us 40 analytes. We had also done some work in the beginning of this sampling effort to look at a more expansive list of 70 PFAS compounds. And just to show you the photos here, this is the treatment system hatches, with that last hatch being the one that we collect the sample from. You can see that aeration occurring when you have the hatch open. And then we use either a bucket grab method or a peristaltic pump to collect each of the samples. Now here I'm showing the data that we have to date for for this site. Concentration is on the y-axis in nanograms per liter parts per trillion, and then we have time on the x-axis, and I've indicated the number of analytes also on the x-axis here for each of the sampling points. And what I have plotted in black is the total PFAS for each sample point. On average, we're seeing about 275 parts per trillion in this wastewater. Again, the groundwater quality standards are between 10 and 20 nanograms per liter, so we're much higher than that in this wastewater. You might notice there's a few kind of points down here that are much lower concentration. There was a pump out of the individual unit septic tanks in this community that occurred in September of 2023. And so we are thinking that the decrease that we see following that could be due to perturbations in the system from that pump out. But as we continue to sample, we'll see whether the concentrations stay steady in the 200 to 300 range or waver a bit more. Of that average 275 ppt that we're seeing, the majority is coming from PFCAs, the perfluorocarboxylic acids that are indicated here in red. The sulfonic acids are in purple, and then precursors are in blue. And of the PFCAs, PFOA is the primary contributor here. We also have some of the shorter chains contributing, PFPEA, PFBS, and then our the most prevalent precursor that we're seeing is 5,3-FTCA with an average of 23 parts per trillion. So now this is concentrations in the wastewater effluent, but one of the things that we're interested in is not just concentration, but actual mass loadings to the environment. And at this, this particular community, they monitor monthly the wastewater discharge flow, and so we can do calculations to understand actual mass of PFAS that's discharged on an annual basis, on a daily basis to the leach fields. So using the flow data, we calculated every day about 67 micrograms of PFAS is discharged per household to these leach fields. You can scale that up annually. That ends up being in the 20 milligram PFAS per household range. And then assuming 3 people per household, that ends up being about 8 milligrams of PFAS per person discharged to these leach fields per year. Now, many of you will know that that's not the entire story, because that's what we can analyze using targeted analysis. But there's also, unidentified precursors that we aren't able to analyze with targeted analyses. So we did the total oxidizable precursor assay for a handful of these samples to understand that unidentified concentration of PFAS that might be in the sample. And essentially we're seeing a near doubling of the amount of PFAS post-top. So there's a little bit more to the story than just the targeted analytes that we were able to measure. So just to summarize, about 275 nanograms per liter is on average what we're seeing in this wastewater effluent, primarily attributed to PFOA, shorter chain PFCAs, and 5,3-FTCA. That ends up being about 8 milligrams of PFAS per person per year. But again, it could be much higher given the total oxidizable precursor assay results that we saw. Now, I mentioned previously that there was a septic tank pump out that occurred in September of 2023. You know, what I just showed here with the concentrations in this wastewater effluent, there is a mass of PFAS that is likely retained in those septic tank solids in the septic tanks themselves that is pumped out on a every 3-year basis that we're not capturing when we're sampling just the wastewater effluent. So we decided to tag on to that septic tank pumping that occurred in 2023 to try and understand what PFAS are we not capturing when we're doing the measurements of the wastewater effluent. So how much PFAS is retained in those solids in the septic tanks that's not making its way out to the leach fields. So we collected samples from 3 of the septic tanks that were pumped, and we collected from each tank both the supernatant, so the liquid that was on the top of the tank, and then the sludge, the solids that settled to the bottom. And we analyzed using APA 1633 and collected the samples with a stainless steel rod attached to a stainless steel cup attached to a rod. And you can see the quality of the samples varied quite a bit depending on whether we were looking at the supernatant or the sludge. So here I'm showing the results from that sampling effort. So each of the tanks on the columns, and then the rows, the top is the supernatant and the bottom is the sludge. And the biggest takeaway here is that we're seeing a lot of variability, both in terms of the concentrations, so ranging in the supernatant from 30 to 930 parts per trillion, and then non-detect all the way up to 246 parts per billion in the sludge. And also variability in terms of composition. So you might notice that tank 2 looks very different than tanks 1 and 3. We did end up seeing, as you might expect, fractionation, where the longer chains in the sulfonates were fractionating to the solid phase, the sludge. And we did also see a prevalence of the FTCAs, as we had seen with the wastewater effluent as well. And similar to the wastewater effluent, we were interested in trying to understand not just concentrations, but also the mass of PFAS that might be retained in these solids. So we did some similar calculations. These calculations required a bit more assumptions, but we estimated between 100 and 3,500 micrograms of PFAS retained in the supernatant in these septic tanks over that 3-year period, and up to 130,000 micrograms retained in that sludge. So if we scale that on a per year basis, that ends up being about 43 milligrams per year, up to about 43 milligrams per year that could be accruing in these septic tanks. But again, we had quite a bit of variability from tank to tank, and that speaks to differences in consumer behavior likely, and consumer product use as well. So in the past few months, we have started using EPA's Emerging Contaminants in Small or Disadvantaged Communities grant program to continue this work and to expand it going forward. So we are interested in how these concentrations and composition will change over time, particularly as we're seeing more and more states enact product bans. New Hampshire just signed into law a product ban this past summer. So we will be continuing to sample at this site to on a monthly basis to see how these concentrations might change over time. And this is just, one of the many sites across the state that have these unique combined septic systems where it's a domestic wastewater discharge. So we will be, and we have just started in October, monthly sampling at an additional 3 sites in the state to see how representative the results are that we have seen at this one community across the state. And one of the things that we've been able to do now that we're using this funding through EPA's ECSDC grant program is to kind of expand that sampling beyond just PFAS. So we'll be sampling monthly at each of these 3 sites for PFAS, but on a quarterly basis, we are also going to be sampling for pharmaceuticals, personal care products, 1,4-dioxane, and some other emerging contaminants to understand domestic loads of those contaminants as well as PFAS. And once we can characterize we're finding PFAS in this wastewater, the next logical question is how can we reduce that load to the environment? So this is the biggest question that we have is, what are the primary sources of PFAS specifically to the domestic waste stream? And we have a 2-pronged approach for this question. In the near future, we're going to be launching a pretty comprehensive off-the-shelf household product sampling regimen where we're going to be sampling a bunch of different product categories so that we can understand where we're seeing PFAS in which specific product categories we're seeing the most PFAS. And then the second piece of this is we're going to be doing some targeted household sampling of the specific household activity, wastewater generated from specific household activities. So I had mentioned, there's all these different household activities that generate wastewater in the home. Which one or ones are contributing the most to the PFAS loading that we're seeing in this domestic waste stream? So I think I'm overdue for a poll question. So that's, I'm gonna let Jennifer put that up. But this is just opinion questions, kind of what we are working towards understanding. So there's no right or wrong answer here.
Great. Okay, I will launch the official one through GoToWebinar. So you can just use your cursor and click on what you think is, what you think from your experience is the correct answer or the most likely answer. We'll just leave this open for a little bit longer. If you are somebody that needs the Massachusetts Licensed Site Professional credits, then you definitely have to answer. But it looks like most people have, so I'm going to close that. Now, the other webinar I did recently, when I tried to show the results to everybody, the screen froze there. We had a big problem, so I'm not going to do that. But it looks like 34% of respondents thought cleaning services was the most contributor, and then 53% said laundry, and then a smattering of people with the other 3.
Nice. Yeah, this is the question that we're trying to answer, and I think many states are thinking about as well. So we hopefully in the next year or two will have an actual answer with data to back it up. So one of the ways that we will, I'm sharing my screen, correct, Jennifer?
Yes, I am seeing your screen.
Okay.
You're all set. Thanks.
So one of the ways that we are trying to answer that question is kind of to step through each of the household activities that generate wastewater, and specifically sample wastewater associated with isolated to that household activity. We have done a little bit of work with household laundry wastewater, where we were testing natural fiber clothes versus synthetic clothes, and with or without detergent, washing with detergent or rinsing without detergent, and sampling the wastewater from each of those treatments, as well as the detergent that was used in that washing, and then the source water that was used to wash as well, and analyzing for 70 PFAS compounds. I'm not going to get too much into the detail of this for the sake of time, but for this particular sampling effort, we found pretty high concentrations of PFAS in the detergent, which was then reflected in each of the wastewater treatments. And, you know, importantly, we found PFAS in the wastewater that was associated with the rinse-only treatments, indicating that PFAS might be leaching from the clothes in addition to being present in the detergent. So and we also, for some of these wastewater samples, also did the top assay to look at unidentified precursors, and found pretty substantial increases in PFAS concentrations using the top assay. So somewhat unsurprising given previous results as well. So we did a similar type of experiment using to look at household carpet cleaning wastewater, with variables being, you know, looking at older versus newer carpet, and with or without detergent again. And again, analyzed the wastewater, source water, and detergent for 70 PFAS compounds. Found again high concentrations of PFAS in the cleaning product that was used, and also reflected in the wastewater generated from each of those treatments. And similarly, the rinse-only treatments also had pretty substantial PFAS concentrations. So, you know, indicating that PFAS are present in the carpets that are, and it's being extracted from the carpets during the cleaning process, in addition to being in the product itself. So these are the types of sampling efforts that we'll be continuing to basically look at each of these types of household activities and the wastewater generated from them, so that we can basically understand the low-hanging fruit of what ways in which we can reduce PFAS in domestic wastewater going forward. I think that is all I have. So I appreciate your attention. I'd be happy to answer questions now, and my contact information is here, so you can reach out after the webinar as well.
Great, Jennifer. Thank you so much. That's a lot of good information. I do just want to comment on the laundry detergent. There was a photo and you could sort of read a label, but I don't believe that was the actual laundry detergent that it was. So please don't try to track that down, because I don't think that was the real laundry detergent that was sampled. There are a lot of questions, and I'll just ask one that I also had, which is the septic tanks, you know, there was that variability between the samples that you got from tanks 1, 2, and 3. Was there any effort to talk to those households that contribute to those tanks and see what differences, or is that future work?
Yeah, so that's one of the things that I would be very interested in doing. At the time, this community has been very cooperative and gracious with us being on the property every month and doing all of the things that we do. And so we didn't think it was a good idea to be, you know, going door to door and kind of putting that burden on the people that are living there. But that is one thing we're going to be doing, some more septic tank sampling going forward, and not at this community in particular, but at others. And that's one thing that I'd like to build into the process, because that's, you know, that's the big question of, you know, what was septic, the house number 1 using that caused those concentrations to be so much higher than the other houses.
Right. Someone's asking if you've got messaging for people that, you know, are on septic and what they should be doing. Yeah, what have you been saying to the public with this information that you're collecting?
So we, for the commercial businesses, small commercial businesses that we have, the carpet cleaning businesses and the schools in particular, we have done quite a bit of outreach to get the word out about what we're seeing in the wastewater, and strongly encouraging them or requiring them, depending, to containerize their wastewater if it contains PFAS, or to treat it prior to discharging to their septic system. We are still in the process of, you know, we haven't quite gotten to the point of the outreach for the domestic wastewater side of things, in part, you know, because we're trying to get ahead of it to begin with. We need to do the work first to understand what particular household activities and what particular products and product categories we need to target at the manufacturer level, and then also at the consumer level. And we just aren't quite there yet. But that's the goal, is once we get that information, then we can, you know, more broadly express to the public what they should and shouldn't be doing and using in the house, and discharging to their leach fields.
Okay, so a couple people have asked this, so I'm gonna have to ask it, which is about what happens to the septic tank sludge after it's pumped out. Where does that stuff go? How is it handled in New Hampshire?
Yeah, so it depends on where the hauler takes it, to a landfill usually, and or to a wastewater treatment plant actually. So it's dependent on what the hauler, whoever is pumping it out, does with it.
Okay, here's a couple of related questions, which is the groundwater, has the groundwater been tested, and does that have PFAS in it? And then if the development is served by groundwater for the water, you know, like, has the water supply been characterized? Is the water supply maybe part of the issue?
Yeah, I assume they're talking about that community. So this is a common question, so I have a slide for it. So here is that community again. each of the houses is served by a private well. And because this is in our groundwater discharge permit program, there are monitoring wells here that are in pink for the groundwater, and everything that is circled in yellow has been sampled for PFAS, and everything is non-detect for all of these samples. They've only been sampled for 4 PFAS, the 4 regulated PFAS. So that's another thing that we'd like to do going forward, especially like at this community and at the others that we'll be sampling, is to look to offer additional PFAS sampling and sample for more than just 4 PFAS. But these are the private wells here are deep bedrock wells, so it's possible that they're not impacted because they are not hydrologically connected to the groundwater discharge at these leach fields.
Okay, let's see. Somebody wanted to know, when was this development built? Is it new or old? And maybe that's part of the puzzle too.
It was built in 2003.
Okay, so pretty recent. Did you find that there was any PFAS compounds that you think are unique to domestic wastewater, or it's really there's not a unique signature for domestic wastewater?
I would say that, as I had mentioned previously, the biggest contributors that we're seeing are PFOA and PFPEA, which that's not particularly unique, but we are seeing 5,3-FTCA as well, which is common in landfill leachate. I think I do have a slide on that somewhere. Down here. So 5,3-FTCA is commonly found in landfill leachate and often comes from carpeting or textiles. So, it's not, 5,3-FTCA is not unique to domestic wastewater because it's in landfill leachate, but it's one of those, it's not PFOA, which is kind of very, very prevalent. So essentially, not at this point, we don't have, there's no particular PFAS compound that we can point to. And especially, I would caution against, this is, again, just one site. I would caution against kind of broadening that out any further than this one location, because as we know, there's a lot of variability in what different homeowners use and how that can impact the signature. So we'll need more data to parse that out.
Right, and somebody's commented that I hadn't really thought of, but also, septic systems are taking human waste, and we know that we have PFAS in our bodies, and also I think I saw somewhere some toilet paper might have PFAS in it. So, but just something to consider is that the human excrement might also be a contributor.
Yeah, that'll be we've thought about that too, but that's a tough one to think about isolating that that particular household activity, but we have thought about that too.
And then somebody was also commenting that there used to be a carpet cleaning business down the road from them on a septic. Do they need to be worried? Seems like maybe they should be.
Yeah, I mean, if it depends, what state they're in, but if they're in New Hampshire, then we should know about it. So.
Okay. Let's see. And someone is also asking about like the floor stripping and waxing and alternatives. So I don't know if you want to mention something that we worked on or not.
Sure. Yeah, so that's a big question that we're trying to answer, you know, because we saw such high PFAS concentrations in the floor stripping wastewater and the strippers and the waxes themselves. We are, you know, trying to get the natural question then is, okay, well, I can't use this, what can I use? And we, NHDES and NMOA, have partnered with a previous project to start to test some of the EPA Safer Choice stripper and wax products to kind of verify whether they are truly PFAS free. There's some other certification programs out there, but very few are focused on strippers and waxes and certifying those, because it's a very difficult product category to remove PFAS from and still have the same performance. So essentially, we're working on doing some product testing for strippers and waxes to verify whether there are some out there that are PFAS free and could be used as alternatives that have similar performance. There's, you know, it's an emerging field. The manufacturers know that this is coming and know that we're, there's a lot of activity in the R&D of these manufacturers to try and remove PFAS from the strippers and waxes. So hopefully in the near future, we will have some.
Okay. Real quick, and then we'll have to move on. Is New Hampshire looking at dry cleaners and laundromats, other laundry places?
So I know we have done some work in dry cleaners in the past. That's not currently an active area that we're focusing on. Laundromats, we have done a little bit of PFAS sampling, and you know, that is one of the areas that we'll be looking at going forward, particularly given the sampling that we've done with the laundry wastewater. So yeah.
Great. All right. Well, I think in the interest of time, we will move on to our next presentation, but Jennifer will still be here. And at the end, we can do some, or she has her contact information in the slides, and folks can get a hold of her separately, but she's doing great work up there in New Hampshire. So thank you.
Thank you.
All right. I'll make the folks in New York the presenter now. And we've got Brittany O'Brien-Drake. She's an assistant geologist with the New York State Department of Environmental Conservation in the Division of Environmental Remediation. Brittany has worked extensively on PFAS impacted sites for the past 6 years. She's got her Bachelor of Science in Geology from SUNY Fredonia and an MS in GIS, Geographic Information Science, from the University at Buffalo. And then we've also got Jasmine Stefansky. She's an assistant geologist, again with the New York State Department of Environmental Conservation and the Division of Environmental Remediation, where she manages a variety of state Superfund sites, including those impacted by PFAS, for the last 2 years. Jasmine also has 5 years of environmental consulting experience prior to moving to DEC. Jasmine has her Bachelor of Science in Hydrogeology from Central Michigan University. Now, before they start, though, we have to do another poll here. So let me set that up. And this is just one to double check that people are paying attention or on. So Jasmine, where did she attend university? The University at Buffalo, Central Michigan University, the University of Michigan, or SUNY Fredonia. So just vote. It doesn't really matter if you get it right. It's just, particularly if you want the Massachusetts LSP credits, you must answer though. So I'll leave it open a tiny bit longer here. And Jasmine was the second person I introduced, and she, just leave it a couple of seconds. Okay, I'll close it now. She was the one that went to Central Michigan University. People sort of were split between the SUNY Fredonia, the University of Buffalo, and Central Michigan. But anyway, it doesn't really matter. So with that, take it away, Jasmine and Brittany.
Okay, I just want to make sure you guys can hear us and see the screen.
I can see your slides and hear you, so you're all set.
Okay, excellent. Thank you for that introduction. I'm Jasmine. I'm here with Brittany, and you'll hear her in a little bit. I am the one from Michigan, so maybe you can tell by my Midwest accent. And I also just wanted to say thank you very much, Jen, for that super informative presentation, and we will do our best to follow that up. Brittany and I are going to be going over a case study each, where we explore the difference between commercial, industrial, and wastewater sources of PFAS. Brittany will be discussing a case study in upstate New York, and I will be discussing a case study from the Hudson Valley. Maybe if I can get the slides to move. I can't. There we go. Okay. Sorry, just as a quick intro, I know that Jen covered this too in her presentation, but as we know, PFAS are found almost everywhere in the environment, and they can enter the environment from a variety of different sources, such as industrial applications, wastewater treatment plant effluent, landfill leachate, biosolid application, and areas of AFFF releases. PFAS can also enter the environment from domestic and residential sources. Brittany and I will both talk about a little bit, and as Jen had mentioned, we use a lot of different PFAS containing items in our homes every day. Certain carpets have PFAS in them, cleaning products, our nonstick pots and pans, water resistant and stain resistant fabrics. When we wash these down the drain, where applicable, where septic systems exist, they can enter the septic system, and septic systems are designed to break down organic matter and not PFAS or artificial compounds. So the PFAS have an opportunity to pervade the septic system and enter the environment. And where applicable, where overburdened geology, where the septic leach fields are located, is in communication with where a drinking water source is located, it has the potential to contaminate that drinking water source. So to help us confirm a suspected link between septic system leachate and drinking water sources, Brittany and I both use septic tracers as a valuable line of evidence in our case studies. This also helped us differentiate between an industrial source of PFAS and a domestic source of PFAS. Brittany and I both chose to use artificial sweeteners, ACE and sucralose, as a septic tracer. Other septic tracers might include nitrates and nitrite. It's important to note, if these are selected for your study, that these are, naturally occurring. It is, however, a much cheaper analysis than the artificial sweeteners, and another septic tracer that could be chosen would be boron. We chose these two as their known presence in food and beverage products. They're not naturally occurring, and they don't readily break down. It's important to note that Brittany and I evaluated these on a presence and absence evaluation, as the relationship between artificial sweeteners and PFAS is not causal. The detection of an artificial sweetener in a sample does not necessarily mean that PFAS will be connected or detected in the sample. As homes have varying frequencies of using these, some people choose to not use artificial sweeteners or use them much infrequently, versus it's very common to have PFAS in homes, and these two compounds behave differently in the subsurface. So therefore, the sweeteners should not be your only line of evidence to differentiate between industrial and domestic sources of PFAS. Before we get started in the case studies, just a little background. Again, case study number 1, which Brittany is going to talk about, is located in upstate New York, where a school at a public well had an MCL exceedance. And the case study I will be discussing is located in the Hudson Valley at an existing state Superfund site, which was previously remediated for chlorinated solvents. And we had a PFOA and PFOS exceedance on site.
Thanks, Jasmine. So before we get into the case study specifics, we wanted to highlight a few similarities between the two. The first being that we have sensitive receptors nearby, including impacted drinking water wells. There are at least pockets of densely populated residential areas, both served by private drinking water wells and septic systems. There was the potential for the geology to support the communication between the overburden where septic systems are and where drinking water wells are set. And of course, we had unknown sources of PFAS, which triggered a source investigation. So as Jasmine mentioned, the first case study that we wanted to get into is located at a school in upstate New York. The school has 2 public supply wells, which were required to be sampled for PFOA and PFOS per New York State's drinking water regulations. Currently we have standards for PFOA and PFOS at 10 part per trillion each. So after they conducted their sampling, they had a slight exceedance of PFOA in one of their wells. This triggered a private well evaluation nearby where some exceedances were also noted. So DEC, or DER specifically, was tasked with trying to identify where is the PFAS coming from. So our first look at this property, we conducted a fairly robust phase 1, and this consisted of, I think, over 20 soil borings or so. Those are shown as the circles on this map, where we collected samples at the 0 to 2 inch, 2 to 12 inch, an additional sample at depth just above the water table or at refusal, that overburden bedrock interface, whichever was encountered first. Where we did encounter groundwater, we did install temporary groundwater wells to get a preliminary look at groundwater quality. And then we also sampled surface water and sediment from the adjacent stream, which is shown on the perimeter of the property flowing north. I'm not going to get into the results of the first phase of work too much, but I just called out a couple that exceeded the New York State drinking water standards. So we had 2 temporary wells that had PFOA exceedances at 47 part per trillion and 22. And then we had a surface water exceedance of PFOS at 11 ppt. So when we took a look at this data, really the detections were relatively low when compared to some of our other remedial sites with obvious sources of PFAS, such as an AFFF site. We have few of those where you have thousands of ppt in the groundwater. However, we did want to take a look, especially around the septic field, a little bit more, and also at nearby potential sources in the area. So we initiated a second phase of work, which was far more comprehensive and expansive. I think we collected over 150 environmental samples. So this phase of work not only focused on the school property, but we also took a look at nearby commercial and industrial facilities, including a manufacturing facility, a waste management transfer station, a former car wash property, a lumber yard, a salvage operation area, and we also wanted to take a little bit of a look into a more densely populated residential area. So what we did on the school property during that initial look, we can also conducted at each of these other potential source areas. So again, that was the soil boring, soil sampling, surface water if it was present, but then this time we did install permanent overburden groundwater monitoring wells to help with groundwater flow direction. But the bulk of our work did also take place in the bedrock. So each of these green locations right here are bedrock well locations. We place these to be nearby potential sources or where impacts were observed. So the bedrock well location on the school property we placed between the school supply well and the septic system. So at each of these green locations, we initially installed a 180-foot open borehole and then performed the standard suite of open borehole geophysics. This allowed us to identify where the fractures were, their orientations, and transmissive zones. Using that information, we packered off up to 4 intervals per borehole to get some preliminary analytical results, which were used to help inform our well construction details. So at each of these locations, we ended up installing a more shallow bedrock well, capturing a more weathered fracture zone. I think those well depths were somewhere in that 30 to 40 foot range. And then we actually installed a deeper well near the bottom of that 180 foot borehole, I think around the 160 to 170 foot range, where we encountered a highly transmissive fracture zone. There was an intermediate fracture zone in the residential area, so we ended up installing a 3rd intermediate well there. So of course, after all of our wells were installed, we sampled them for PFAS, but we also deployed transducers after the fact and left them in for a month or so to assess water levels over time. So now I'm going to walk you through the lines of evidence that we used in this investigation that we gathered, which support multiple non-discrete sources of PFAS in the area, but including that septic system or wastewater source. So this first line of evidence is looking purely at the detections. Again, these were relatively low across the study area, nothing jumping out glaring as an obvious source that we could remedy. However, the highest detections were observed on the down gradient side of the school septic system, where combined concentrations of PFOA and PFOS were around 70 parts per trillion. Soil data was even less indicative of a source. We only had 1 soil sample that exceeded our residential use soil guidance values, and that seemed to be very discrete as concentrations decreased with depth significantly, and there were no real high-level groundwater impacts nearby. So we have low-level detections in both soil and groundwater and surface water, nothing that we could point out as the specific commercial or industrial source. The next thing we did was we took a look at the geology. We installed all of those wells, performed open borehole geophysics and such. So our conceptual site model showed that we had a thin overburden layer across the entire assessment area underlain by a shallow shale bedrock. The geophysical data told us that there was a shallow weathered fracture zone, again around that like 40 feet maximum depth range, and then a more highly transmissive primary fracture zone towards the bottom of each of those boreholes around that 180 foot mark. It's likely that all of the drinking water wells in this area intersect that primary transmissive fracture zone. And here, unlike sandy aquifer, where you may have more of like a bathtub of water that can more quickly dilute contamination, here the water bearing zones are more discrete, resulting in similar PFAS concentrations in our shallow wells as well as the deep zones. I had mentioned that we deployed transducers, so I just wanted to pop up one of these figures to also show the connection between the surface and the deeper fracture zone. So the orange lines here that you can see is our water levels in our deeper bedrock well. You can see strong influence and change in the water levels from the school's pump turning on and off. The yellow line on the top of your screen is the water levels in our shallow bedrock well, and then the blue is precipitation data. So just looking at the shallow and deep wells, you could see changes in water levels as the pump turns on, you do see a decrease in the shallow as well as the deep, and a similar increase in water level when the pump turns off. And then, of course, more obviously, the precipitation data, we had a high precipitation event, and we see increases in water levels in both the shallow and deep bedrock wells, which both confirm the connection between the surface and the bedrock, as well as between fracture zones. Our third line of evidence are the PFAS fingerprints. I'm just showing one's fingerprints from the school property and not the other properties, but this will drive the point home well enough. So on the left-hand side of your screen, this is the fingerprint from the school supply well. This has a signature that is more rich in 5 and 6 chain carboxylates as well as PFOA. The plots here up on the top side of your screen are from the bedrock wells, and then a few from around the school septic system. Again, these all have a similar signature rich in those shorter 5 and 6 chain carboxylates as well as PFOA. On the school property itself, these signatures are similar, indicating a similar source, which again we suspect was the septic system. Where we could perform fingerprinting on the other properties, there were simply, in some cases, not enough PFAS, only a few PPT detected, so we can't perform fingerprinting there. But where we could, the patterns were not the same, indicating that we have multiple non-discrete sources of PFAS in this study area. And our last line of evidence, which Jasmine alluded to earlier, was the use of artificial sweeteners as a septic tracer. We sampled for artificial sweeteners in surface water, in our overburden wells, as well as our bedrock well couplets, so those shallow and deep wells, and additionally in some of the drinking water supplies. And we ended up finding sweeteners in all media that we sampled, with the highest detections being on the down gradient side of the septic system in the overburden well at around 12 ppb. We did see concentrations of sweeteners decrease with depth. However, they were still present, which further supported the connection between the surface and the bedrock. We did sample for nitrates. I don't have it on the screen, but the results were fairly similar, with highest levels of nitrates being on the down gradient side of the septic, and then also decreasing with depth. Just to wrap up case study 1, again, we ended up concluding that we have multiple low-level contributors of PFAS to the environment, including septic systems. This was supported by all of the geology information we gathered through the geophysics, transducer data, and then of course looking at the analytes themselves, the PFAS fingerprints being similar on the school property and around the septic, different elsewhere, relatively low concentrations across the study area, no real hotspot that we could remedy. And then we used the artificial sweeteners to assess whether or not there could be the potential for PFAS from the septic systems, as Jasmine and Jennifer talked about in her presentation, entering the environment via the septic system. So that wraps up case study 1. And Jennifer, I don't know, is this a good spot to do the next poll question?
Yes, this is perfect. So here's the question, and now I'll launch it here from the go-to site so you can answer. So which septic tracer did Jasmine and Brittany use in their case studies? PFAS, artificial sweeteners, boron, or dye? So everybody can just vote, and if you want the Massachusetts Licensed Site Professional credits, you must vote. Otherwise, it's optional, but you may as well do it. And we'll just leave it open. I think we've got a lot of answers, and 98% of the people picked artificial sweeteners, which is what, oops, they did use. And I didn't mean to share the results because that could create a problem here, but hopefully, oops. Okay, there, it seems to be working. Okay, we're done. Take it away, finish up. Thanks.
Okay, all right, it is my turn, and I'm going to go over case study number 2. Again, this one is in the Hudson Valley at an existing state Superfund site. This site was a historical dry cleaning operation, and it has been remediated for chlorinated solvents. Under the Emergent Contaminant Sampling Initiative from New York State, we were directed to go back to existing state Superfund sites and sample for emergent contaminants, so PFAS. So we went out in October 2020 and sampled for PFAS on the on-site groundwater wells, and we discovered that we had detections above the MCLs, had a concentration. The highest we saw was PFOA at 99 and PFOS at 52. We compared these groundwater samples to the drinking water MCL of 10 ppt for both PFOA and PFOS, as at the time of these samples, the groundwater standards weren't promulgated yet. Due to these exceedances that we saw on site, we were directed to survey the surrounding area for any potential sensitive receptors, including private drinking water wells. And we discovered that 50% of the population in this area uses private drinking water wells and private septic systems. So we offered sampling to the homes of private drinking water wells within a half-a-mile radius around the state Superfund site. And we ended up sampling 219 homes, 203 of which exceeded the MCL for either PFOA or PFOS, so about a 90% exceedance rate in this area. And the maximum detections we saw in the residential wells were PFOA at 47, PFOS at 85. As you can see, a pretty similar range to what we were seeing on site in the groundwater wells. And therefore, that led us to believe that the Superfund site was not the only contributing source or the contributing source of PFAS in this area. So we also moved forward with a source investigation. Before we get into the selection of our sources that we investigated, this area has very thin overburden underlain by fractured bedrock. The majority of the private residential wells are screened within bedrock. This area used to be a vacation home destination, but now we have people living there more frequently and year round. So that means using the private drinking water wells more often, using those private septic systems more often. It's just a little background about the area we're looking at here. So we initiated a desktop study and we ended up identifying 12 potential sources of PFAS in the area. We investigated industrial sources, waste management areas, and areas of known fires, which included some of the marinas due to potential boat detailing chemicals that are used in that process, areas of known fires where AFFF could have been released, the fire department where AFFF could have been stored, areas of waste management such as the effluent from the wastewater treatment plant. And we also looked at on the peninsula, this is the area that is most densely populated, and all homes on the peninsula use private drinking water wells and septic systems. So we also installed some overburden monitoring wells on the peninsula to evaluate potential domestic wastewater sources of PFAS in this area. So here's some select source investigation locations where we took groundwater samples at. We took over 100 samples of environmental media throughout the whole investigation, which included groundwater, soils, sediment, and surface water where applicable. So here are 4 of the source investigation locations, and I put this on this table here so that it could be compared to the concentrations of PFOA and PFOS seen in the private drinking water wells and also in the groundwater wells from the on-site state Superfund site. As you can see, the concentrations are all basically within the same order of magnitude. We don't have anything over 100, which also led us to believe there's some sort of ubiquitous source of PFAS in this area due to all of the concentrations being relatively similar. We moved forward with PFAS fingerprinting to see if we could find a unique source in this area. So there's a couple slides I'm going to click through here, but the first slide, here's the location of the state Superfund site. These were the signatures that we found from those on-site wells. I'm adding in some of these signatures from selected source locations that we analyzed for groundwater at. As you can see, the ratios of PFAS signatures are relatively similar to one another. Then I'm adding in the private drinking water signatures now. Again, we sampled 219 wells, so obviously cannot put all those signatures on this figure. So there's a selection of a couple. And then this figure over here, the signature is a composite fingerprint for 91 of these sampled wells. Then the last signatures I'm going to throw up on the screen here include the lake surface water sample signatures and also the signature from the wastewater treatment plant effluent. Just to go into this a little more and highlight this, we see the wastewater treatment plant effluent has a very similar signature to the drinking water composited sample from those 91 drinking water sources. The wastewater treatment plant effluent we used as a proxy to represent a domestic wastewater source in this area, as 50% of homes still use the municipal sewer. And so with that comparison to the drinking water composite sample, and then again, the samples taken on the peninsula, these were the 2 installed overburden groundwater monitoring wells to also help us assess if domestic wastewater was a contributing source in this area. We further analyzed for artificial sweeteners to help us confirm that link between the septic systems and drinking water sources. We sampled artificial sweeteners at 7 of the drinking water wells and those 2 groundwater wells we installed on the peninsula. You can see we had artificial sweeteners detected in every single sample that we took. I'd like to also take a second here just to highlight again that artificial sweeteners and PFAS don't have a causal relationship. If you look at PWO3, the detection of sucralose is the highest sweetener, and this does seem to correspond to the highest detection of PFAS. However, if we were to look at PWO1 results, we have elevated PFAS, but we have some of the lowest detections we see of artificial sweeteners. So therefore, again, this should not be used as your only line of evidence. So our conclusions for case study number 2, which lead us to believe that there are multiple low-level contributors of PFAS to the environment in this area. We don't have a point source necessarily, and it includes domestic wastewater. It's supported by the geology that allows communication between the overburden and the drinking water source. The fact that this area is very densely populated with 50% of the population using private septic systems, the similarities in PFAS concentrations and signatures between the on-site groundwater wells, the source investigation areas, the private drinking water wells, and the wastewater treatment plant effluent, and that septic tracers were detected in this area.
All right, so we'll start wrapping things up here. So as we all know from both presentations today, PFAS are used in a wide variety of consumer products. Therefore, low-level detections of PFAS may not always be attributable to a commercial or industrial source. Both of these case studies will be used going forward to inform actions at other sites where similar conditions exist. Again, those being the lack of an obvious or readily identifiable commercial or industrial source, areas that have private septic systems where the geology is conducive for supporting the communication between these septic systems, and where drinking water wells are set. If we do suspect wastewater is a source and are doing an investigation, we are going to be considering adding in septic tracers to the analytical plan. This again may include artificial sweeteners or others we didn't really get into today, like nitrates or boron. And then again, the PFAS fingerprints were also very useful in both of our case studies in determining if one or more sources were present. So we always get questions about how did the public respond to this? How did you communicate your results? So both of us learned very early on in our investigations that consistent communication was key. So we achieved this through issuing fact sheets or community updates regarding the investigations. This allowed the community to start digesting results in smaller bite-sized chunks rather than just a huge long report that no one wants to read. We also had fact sheets available for PFAS in private wells or in where it's found in consumer goods, that sort of thing, treatment systems. But we also found that having availability session style community meetings was very effective, rather than perhaps a more traditional give a presentation and an audience and then having those ask questions. These sessions were set up in broken up into sections. So we have investigation tables, we have health department tables, we have water treatment tables. That way members of the community could come in and ask questions directly with our technical experts, more on that one-on-one type of setting, or at least in smaller groups. We found that to be very effective in our messaging. And then of course New York has the ability to set up some web pages for sites as needed, or we really like to use the DEC info locator. This is an interactive map and kind of data warehouse where the public can go on and look up our remedial sites, zoom in and click to the online database that's been set up for each of those, so they can review final work plans and reports at their leisure. This sort of ties into the public relations piece, and the short-term recommendations from both of these investigations was really focusing on education and outreach, encouraging private well owners to routinely sample their private wells, not only for PFAS, but for any other contaminants of concern as recommended by the state and local health departments. And as Jennifer had mentioned, proper maintenance of your septic systems, routine pump outs may help address some of that PFAS entering the environment. And then we haven't done this quite yet, but certainly for the school or other big box store type facilities that have septic systems, we may want to consider managing the wastewater that's leaving those facilities and likely where the mass of PFAS is coming from. As with everyone else, New York is looking towards longer term solutions, including removing PFAS from the environment, which obviously is easier said than done. But we are currently controlling industrial discharges through our SPEEDIES permit system. We're working towards identifying and remediating PFAS contaminated sites, enacting laws and regulations aimed at manufacturers who use PFAS, phasing out intentionally added PFAS in consumer goods, and offering take-back programs of PFAS containing materials. So this last slide, which you guys will be able to click on later, is just some links to some of the topics New York is doing and perhaps things I'm not as well versed in. And there is our contact information. So that's all we have. Thank you so much.
Excellent. Well, another great presentation with a lot of good information. So there's quite a few questions again. Some of them are around the artificial sweeteners. Can you just talk a little bit more about the logic for using those? How do they travel in the subsurface, and do they break down, or what's the logic for them?
Yeah, I'm not well versed in all of the chemistry and super detailed fate and transport topics, but it's our understanding that they don't break down super readily like caffeine. We looked into using caffeine as a tracer, but it seemed like that broke down more easily. The sweeteners we had read about in a couple other research papers and decided to use sweeteners as they're not likely present in the environment in any other capacity. Maybe you have some historic landfills or something, or a manufacturer of sweeteners, but in this case we did not have those immediately nearby. So we thought the sweeteners would be a conservative tracer for us and a really easy concept to relay to the public of presence absence evaluation and where those come from.
Okay, and also it's just because it's naturally sort of in domestic wastewater. It's not like you're adding it on purpose, right, during the investigation. Yeah. And what does the analysis cost? People are wondering.
I'm not sure if I'm allowed to say. It's expensive. You can reach out to Eurofin's lab. That's who we went through for the analysis. So it may not be a great option for everyone. So maybe you could explore sweetener testing for some locations and maybe look into those cheaper analyses for others like the nitrates and boron, but it's not cheap.
Right, okay. And somewhat related to that is, these investigations were both funded by the state of New York, or is there a different mechanism?
Yes, these were both state funded.
Yes, and as you can see, you know, I did not sample the sweeteners at all of the 200 wells. We had to get a very small subset of that.
Okay. Let's see. In the first case study, fingerprints were similar in septic areas and elsewhere at the school. How did the fingerprints in the samples from the off-property at the commercial and industrial properties compare? Were they noticeably different fingerprints?
Yep, I don't remember exactly which compounds were higher, but the signatures were not similar, so that led us to believe there were different sources. And even on the other properties, the total PFAS on those were very low, like I think in most cases, or in a lot of cases, like that 20 ppt-ish range for total, or maybe a little higher. So once you get down into those low ppt ranges, fingerprinting becomes a little less useful.
Okay. Let's see. Lots of things about those sweeteners here. Okay, this work suggests cleaning up low-level contamination would be very difficult without eliminating PFAS from consumer goods. Like, there's no plans currently to initiate some sort of remediation at either one of these sites, or is there?
Correct, yeah, and the DER's program, Division of Environmental Remediation, we're really focused on cleaning up commercial and industrial sources of PFAS. Like we have sites with 30,000 ppt in the groundwater from AFFF use, or PTFE coders with 20,000. So in our division, we're targeting commercial and industrial sources that we can target cleanup actions at.
Right. Let's see. People are wondering about sort of, because the drinking water has some PFAS in it, then it's sort of cycling around and maybe concentrating that way. Or are you feeling that it probably has something to do with these consumer products?
Yeah, at the school case study, we're pretty confident it's coming likely from the school's cleaning operations, the waxing floor strippers and such, and it's entering the environment through the septic system. I see where I think the question may be getting at, like, how do you know it's not coming from elsewhere in the groundwater? We kind of rolled that out through looking at other nearby potential sources and assessing groundwater quality off the property. But yeah, you're right, it's kind of like a vicious cycle, right? It's being taken in by the supply well, back into the school, back to the septic field, and so on. Yep.
And that's kind of at my case study as well. You know, we have such a densely populated area with so many people using those private drinking water wells and septic systems. I mean, I think that is part of the reason we saw such a similar signature across the board, because that was all getting, you know, homogenized by the relatively continuous pumping and release of those PFAS.
Okay, folks are wondering about, so at situations where there is an industrial source or a site or a suspected source, how are you taking into account this domestic contribution as well? And is there a way to distinguish? Is there some, I guess the fingerprinting you may or may not to show something to distinguish?
Yeah, it's definitely all site specific, but typically with our remedial sites, it's fairly obvious where we could see concentrations at the source, and then they taper off with distance. And you know, that also is a compounding factor with the fingerprinting. As you move away from the source, you've got, you know, the retention of maybe more of the sulfonates, and transformation of precursors and intermingling sources. So it's certainly a challenge, but there's definitely tools in the toolbox, hopefully, that you can kind of parse out between your site data and elsewhere.
Okay. All right. Well, basically we're at 3. There's still a few other questions here, but so
Folks
this
can
would be for,
definitely reach out via email too.
yeah. Well, I'll just ask this last question here of both New York and New Hampshire, which is just, what resources are there for the public? If you're a homeowner and you're concerned about your water, do you have suggestions for them for what they should do and how to do it? Are there any resources like fact sheets or something?
Yep, New York currently, we have several fact sheets that there might have been a couple on that last slide with guidance to homeowners on sampling, what laboratories to use, and different filtration options, whether that's a point of use or a point of entry. Everyone's budget is different and such, but we really encourage homeowners to reach out to their state and local health departments as well to help with that sort of thing.
And
Yeah,
on New
folks.
Hampshire
Oh, go
side,
ahead.
basically ditto. We also have plenty of fact sheets that are on our website that can help with all of those questions. And I think what I'll do is I haven't sent you the PDF to post yet, Jennifer. And so when I do that, I can include some of those links so that it's easier for folks to see.
That would be great. Yeah, people are wondering about how to refer, homeowners to labs. And a couple people are commenting that it looks like they artificial sweetener tests maybe were in the $500-600 a sample range. I don't know if that's anywhere like what New York found, but somebody mentioned that.
Yep, that's a good ballpark.
Yeah. So yes. Okay. Well, yeah, since we're 2 minutes after 3, I think we'll end this. But this was great. Thank you so much, Jennifer from New Hampshire DES, and Jasmine and Brittany at New York State DEC for all the great work that you're doing and that you're going to continue to do. And we will probably try to have a webinar in the future where you can update us with what you're finding. And with that, thank you again to everybody, and I hope everyone has a nice rest of your day. And also, we're in the holiday season. It sort of snuck up here, but hopefully everybody has a nice holiday season here. And I'm going to end the webinar for everybody. Thanks again.
Thank
Bye-bye.
you.